Hi, welcome back to es346 Basic Thermodynamics. This is module 8.1, Total Reversible Work. The section of the textbook is section 8.1. So here's our course outline, and we've got to the end here. We're at our very last module, module 8, and our topic is exergy. And exergy is really interesting because it's actually a combination of both the first law and the second law. We'll realize that it's a property that accounts for the conservation of energy and at the same time accounts for the fact that entropy must increase or at best remain zero. So here are the two learning outcomes for the module. At the end, you'll be able to calculate the reversible heat engine work for a finite temperature source, and you will also understand how the total reversible work between two states is path independent. So first I want to talk about finite heat sources. We've looked at this kind of idea where we put a heat engine between infinite heat sources and infinite heat sinks before. Infinite meaning that as I went ahead and removed some amount of heat QH here, this source was able to remain at TH. What I want to look at now is the case where this is finite. So as I remove TH, or as I remove QH, the temperature slowly drops. Now we'll go ahead and keep our sink as an infinite sink at this point. Here's the work being generated. But we're going to consider the source to be finite. So as I remove QH, temperature drops, and if I want to know how much it is, I can write a first law energy balance. It says QH is equal to mc delta T. That would be delta T of the high temperature source. And the efficiency of this heat engine is going to change as TH changes. So we know the efficiency of the heat engine is the work over QH. Now, QH is changing, so we're going to have to go ahead and do an integral of that. So let's consider a differential change in QH. That will make this equal to dt. And I can write my efficiency as del W over del QH. Now, if I want to go ahead and rearrange this equation for del W is equal to eta del QH. And now I'm going to substitute in this expression there, so this becomes eta mc dt. Now, the efficiency, the maximum efficiency of a heat engine would be a reversible heat engine, where the efficiency would be equal to 1 minus TL over TH. And so I'm going to go ahead and put that in for my efficiency up here. And so now I've got del W is equal to 1 minus TL over T mc dt. Now, I wrote this as just T because this is TH, but it's changing with time. And now what I can do is go ahead and integrate this. I can integrate it from its initial temperature, I'll call that TH, to its final temperature. Well, this heat engine could keep operating until I get down to TL, at which point those are on the same temperature. So my integral is going to go down to TL. So I'm going to go ahead and integrate this expression, and what it comes out to be is the work is equal to mc, and it is TH minus TL, natural log of TH over TL. So you can go ahead and confirm that calculus if you want. And this right over here is the amount of work, the maximum amount of work, because I went ahead and assumed it was a Carnot engine there, so I'll go ahead and call this reversible work. The maximum reversible work I can get from a finite heat source. And this is going to be important for the next analysis that we do. So what I have here is I have a piston cylinder. It contains 1 kilogram of air. It's at 300 degrees Celsius and 300 kPa. And what I want to know is what's the total amount of work I could get from it? Well, I could get work from a couple ways. I could hook a heat engine up to it because it's hot, or it's also pressurized at 300 kilopascals, so I could go ahead and allow it to expand and do some boundary work and get work from it that way. And so I need to know what my environmental conditions are to know if I'm going to be operating heat engines and pushing the piston against the environment. So here are my environmental conditions, what's outside the piston, 25 degrees Celsius and 100 kPa. So let's go ahead and calculate the amount of work that we can go ahead and get from this. So first what I'm going to do is I'm going to put some little, let me go back there, put some little stoppers on here to restrict this from moving. And I'm going to go ahead and hook a heat engine up to it and pull heat out of it. It's at initially at 300. Generate some work, and then this is going to go into T low, which is at 25 degrees Celsius. So there's my work, and there's the heat. Now this is that finite temperature source, because as I pull heat out, I've only got 1 kilogram. It's going to drop from 300, and I can go ahead and operate it until it gets all the way down to 25 degrees Celsius. So if I want to know how much work that is, we just saw that equation. That work is equal to MC pH minus TL natural log of TH over TL. So let's go ahead and put some numbers in there to calculate that amount of work. And I have 1 kilogram. This heat capacity, I'm keeping the volume constant, so that's going to be C sub V, so 0.718. That's CV of air. And then my temperature, and these need to be absolute, so 573 minus 298 natural log of 573 over 298. And that's the amount of work this heat engine is going to go ahead and generate. And when it's done with this, it's going to be down at 25 degrees Celsius, completely spent. And that amount of work is 57.56, and that is kilojoules. All right? So now the question is this completely expended? Is there no more work I can get from it? Well, it's at 25 degrees Celsius. I can't use a heat engine, but maybe it's still pressurized. I don't know, since I went ahead and kept this volume constant. So let's go ahead and find out what the final pressure is. So I can use the combined gas law. P1 over T1 is P2 over T2 because the volume was constant. So that means I'm going to have 300 over 573. So the initial pressure over the initial temperature is equal to P2 over 298, which is the final temperature. I can solve for P2 from there. And P2 is 156 kilopascals. So although it's at 25 degrees Celsius, it's still pressurized to the outside. So I could now remove these stoppers and go ahead and have it do some more work. So let's go ahead and do that step next. All right, so here's the first work that we got. And now we're at 25 degrees Celsius, but we're pressurized at 156. And what we're going to do is we're going to let this now remove those stoppers and let this push back, and we'll go ahead and get some work from it until it goes down to 100 kPa. So what we need to know is how much work it's going to do, how far up here it's going to go, what's V2. And the maximum work we could get would be isentropic expansion. So we call the equation for isentropic expansion would be V2 over V3. I'm saying that I'm starting at 2, and now I'm going to 0.3 because we already had a condition 1. To the exponent k is equal to P3 over P2. And so this P3 is going to be 100 kilopascals, and it starts off at 156. So I can go ahead and now solve for what my volume is going to be when I'm done with that expansion. And V3 is going to be 0.532 meters cubed per kilogram. We have 1 kilogram, so it's actually 0.532 cubic meters as well. So now I know where it's going to go from V2 to V3. So let's go ahead and get our work for this step. I'll call this W2 because this is the second step that we're doing, going from 2 to 3. And that is going to be the mass times, we've got P3 V3 minus P2 V2 over K minus 1. This is the reversible work that it can do. Now, another thing I need to remember, if I want to know how much usable work I can get, pushing back the atmosphere doesn't do any usable work. So I need to go ahead and subtract off the atmospheric pressure, that's P naught, of 100, and that volume change, so V3 minus V2. And so the mass is multiplied by all of that. So go ahead and give me the amount of work I can get from this next step. And that comes out, if you do the arithmetic, is 5.02 kilojoules. So this is some additional work that I can get. I'm now at 100 kilopascals. And the question might be, well, what's my temperature at this point? Because if I went ahead and did isentropic expansion, that means I didn't have any heat transfer. The temperature could have changed. Let's go ahead and calculate what our temperature is, T3. T3 is P3 V3 over R. And if I do that, that is 263 Kelvin, or minus 10 degrees Celsius. So I'm actually now colder than the environment, which puts us up a pretty interesting situation, because now what I can do is I can go ahead and put another heat engine in here, where now I'm going to pull energy from 25 degrees Celsius and put it into minus 10, and I can actually generate yet additional work. So we can keep using this device. Let's go ahead and do that next step. So now we're at minus 10. We've got our heat engine, and it's generating work coming in, the high temperature source in this case is 25 degrees. The low temperature sink is minus 10. And here's the work in the first step I did, the work I did in the second step, and now I've got a third step of work that I can do. And you kind of probably already starting to realize that you can do this for quite a while. So what I'm not going to do this time with my heat, I've got a heat engine. I'm not going to put the stoppers on, and I'll go ahead and let this volume change. In fact, it's going to end up getting a little bit larger. So I'll do it at constant pressure. So at the end, I will be at this conditions right here. So that amount of work with that heat engine is MC pH minus TL natural log of pH over TL. And this will be C sub P because we're going to be doing this at constant pressure now. So let's go ahead and put our numbers in for that. And if we do, we find that we need to find out what our last temperature is going to be. The last temperature is going to be 298. We're starting off at 263. And so P naught is equal to 298, which is equal to T low. Alright, and now if we calculate the amount of work we get on that step, that is 2.23 kilojoules. I'll call it W3 because that's in our third step. So now let's go ahead and sum up the work. The total amount of work we did, we're now at what I'm calling the dead state because we're also at 25 degrees Celsius and 100 kPa. We had 57.56 kilojoules. The next step gave us 5.02 kilojoules. And the next step gave us 2.23 kilojoules. And that total was 64.8 kilojoules. So that's the amount of work I can get going from initially 300 kPa and 300 degrees Celsius down to these conditions right there. Alrighty, let's think about this. Now, there was all these different ways we could do it. We could hook up the heat engine, we could go ahead and do the expansion. And my question now is, what if we did it in a different order? What if we went ahead and did the expansion first? So maybe I'm going to go, and now, instead of doing the heat engine in the first step, I'm going to go ahead and do the boundary work over here. So I'm going to go ahead and drop from 300 kPa to 100 kPa. So we're starting off with our initial volume, which is our T1 over P1, and that is 0.548 meters cubed per kilogram. We have 1 kilogram, so it's 0.548. And to go ahead and find V2, we'll go ahead and do our isentropic expansion again. So V2 over V1 to the K equals P1 over P2. And the initial pressure is 300. Final pressure we're going to is 100. And now we can go ahead and find out what V2 is in this step. And V2 is 1.2 meters cubed per kilogram. So the work we get in that step is equal to P2 V2 minus P1 V1. This is isentropic expansion, so K minus 1. And I need to subtract out this work pushing back the atmosphere, because that doesn't really do us any good. So V2 minus V1. Need to multiply all that by the mass. And now that's going to be 45.43 kilojoules. So it's a little different than any of the other steps that we have. Now we're at 100 kPa. But maybe we've got some additional thermal energy in there we can use. So let's calculate what T2 is. T2 is going to be P2 V2 over R, and that is 418 Kelvin. Clearly still hot. We can still go ahead and hook a heat engine up to this. So let's do that second step. So here we are. There's our work from the first step. We're now at 145. That's 418 Kelvin. And we're going to go ahead and now hook up our heat engine to it. Generate some work from there. There's our QH. We're going to dump this into this 25 degrees Celsius sink. And let's go ahead and do this at constant pressure so we don't run into that problem where we kind of got an infinite loop last time. So here's my work. It's MC, we're doing this at constant pressure, C sub P. This will be T2 minus T0. This right over here is on T0, the environmental conditions, minus T0 ln of T2 over T0. And if I sum up that work, that's 19.16 kilojoules. So not sum the work, do the arithmetic with those numbers. So now we're at the dead state because we went ahead and allowed the pressure to remain constant. So doing it this way, our total work is equal to this 45.43 we did in the first step, and the 19.16 kilojoules we get in the second step. And if I add those two numbers, I get 64.6 kilojoules. Now that is suspiciously close to the value I got last time, although I did it in an entirely different sequence of steps, going at some different intermediate parts as well. And that's pretty interesting, and I think at this point you kind of see where we're going with this. So what we did, let's kind of think about that first process we did. We started off at this high pressure, it was about 300, and we went ahead and hooked the heat engine up to it. We kept the volume constant. We got some work. We went to this point there, and then we went ahead and did some boundary work expansion. We went there, and then we went into a heat engine. This is when it was cold, -10, and we let it expand to that point. And each one of these had some work. There was a work 1 there, and a work 2 there, and a work 3 there. And we add those up, and that was at 64.6. Now the second time, what we did is we went, and we first did this expansion, so we went to that point, and then we hooked up the heat engine and went to that point. So there was work 1, I call it work 1 prime, work 2 prime. Now when we summed up this and this, we got the same value as these. So it's interesting because work is path dependent as I go to a particular point. But it appears the summation of all the work from one point to another point appears to be the same every time. And I think at this point you know exactly what that means. That must mean the total reversible work between points is a property. And it turns out it is, and that's the exergy. And that's what we're going to go ahead and derive in the next module.